Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about dark matter and why it's not needed. I'm going to compare that to G, the gravitational constant, and see which one, dark matter or G, might be the answer. Now, this becomes a problem because when scientists measure the velocity of the stars at the edge of the galaxy, they get a number that is too high compared to their calculated number. Now, this is a typical graph, one I'll be using throughout. It has a vertical axis, which has the velocity in kilometers per second. It has a horizontal axis, which is in light years. And right here on here is showing where our solar system is, how far it is from the core. It looks like about 24,000 light years. The blue curve is the measured values, the typical measured values. The red curve is the calculated values using the Keplerian equations. Measured values too high, calculated values too low, there's a problem. So there are other graphs just like that. You can see this one from Arizona University, and it plots a blue line just about the same way, but you can see some of the dots it used and how it weaved the line through these dots, depicting a typical value, even though the measured values vary around that. Here's one from Ohio State. That green line looks basically flat, and there's the red line, which is the Keplerian prediction. But even with the green line, if you look, you can see that it's moving up and down, but that's the way they plotted it. So you can pick and choose which graph you want to look at. I picked the first one and move forward with that one. Now, this is the equation that you use to calculate the velocity of an object if it is going to orbit. It must have this velocity at this distance if it's going to orbit the galaxy. And of course, when they calculate this velocity using Newton's gravitational constant, the mass of the galaxy divided by the distance between the core of the galaxy and the location of the object they're measuring, they get a velocity and the value is too low. Value is too low. Somehow they need to increase this value. So they look at the three terms, Newton's gravitational constant, the mass of the galaxy, and the distance, and which one of these might be out of whack. Well, they look at G, and they really can't increase G. They are convinced that Newton's gravitational constant, it is a constant. You say, well, it's probably not a good thing to change that because Newton's equation works, at least in most cases. So they can't do anything about that. So what about remeasuring the value of the distance? Well, they could probably do that, but they're probably going to end up with something very similar and not enough to explain the difference. So what they're left with is the mass. And if you want the velocity to increase, you can either increase G, which they say they can't do, decrease R, which they say they can't do. So they're going to say, wait, maybe I can do something about mass. Maybe there's a mass out there that we don't know about. So they modify the equation and they put two masses. M sub v is the visible mass, M sub d is the dark matter, and they're going to estimate somehow, and I'm not going to go through all this, but they do that and they come up with this result. This is a copy out of Wikipedia. Not going to go through all of that, but I highlighted in red the amount that they're saying is ordinary matter. 4.9% is ordinary visible matter. 95.1% is dark matter or dark energy. However they come up with those numbers, that's what they need. Look at the ratio. 95% is 19 times the value of 5%. This value of dark matter is 19 times the value of the visible matter. That's a lot of matter just to make this value come up. And when they do that, when they may add this, they got the right velocity. Their solution to maintain G and to maintain the distance, they have to invent dark matter so that Newton's equation is still valid, and it's valid at the edge of the galaxy. They don't say much about the blue curve, just the edge of the galaxy. Okay, so now I'm going to explain this blue curve a little bit using G1 gravity. The particle model has three main particles: the nucleon, which replaces the neutron and the proton, and it has the G1, which replaces the electron, photon, and graviton, and of course the G2 is the force, is the particle that is responsible for the nuclear binding force. Regardless, particle model uses G1 gravity, gravity 1. So we're going to explain this curve, and I'm going to explain it by looking at this picture. In this picture of our galaxy, the graphic, the yellow part is the core, and coming off of one edge of the core is one major arm, and coming off the other edge of the core is another major arm. We have minor arms in between, there and another one here, but for the analysis I'm going to only concentrate on the core, the first arm, and the second arm. In this graphic, there is a polar grid whose center is located right here, and is located right on our solar system. And what you'll see is as you go from the core through the first arm, then between the first arm and that second major arm, these are major arms, is our solar system right there. Okay, so we have this image now of the galaxy as a core and two major arms. So now I'm going to walk you through this blue line, visualizing the galaxy using the blue line. Okay, so again, we have the velocity in kilometers per second. We have the distance in light years, and this is the location of the sun, which is in between the first arm and the second arm. And so let me show you how we get there. At the core, the velocity of the objects right at the center of the core is 0. This is much like if you take the Earth, my hand, and you're standing on the North Pole. Even though the Earth spins, your velocity is almost 0. Okay, at the edge of the Earth, it's very high, much higher. And that's what you have here. You have the velocity at the center of the core going up to a peak at the edge of the core. So this represents the velocity through the core out to the edge, where you have a peak of around 250 kilometers per second. This is the gap between the core and the first arm. And it tends to drop very much like 1 over r squared. If you could take this curve, put it over here, and just draw another curve moving down. And that's what it would do. So this is dropping like r squared. Then it reaches the arm, and then it increases. This is the first arm. Then it falls after the first arm. We reach our solar system right here. And then this drops. Now this doesn't drop as much, presumably because there's more mass out there, more objects. And as a consequence, it's a compromise between dropping like r squared and moving up. But it drops. And then this is the second arm. And then from there on, you're outside the galaxy. You can actually see our galaxy. You can visualize the core space, arm space, arm, and you can see it in the blue curve. It's literally staring you in the face. Now, the particle model's answer to this is that we have a G1 force field all the way around the galaxy. And this force field is set up by particles passing through the galaxy. And I'm taking, in this case, the galactic plane. This is the galactic plane. Now, these forces come in all directions, all X, Y, and Z directions, three-dimensionally. But for the analysis, I'm only going to use this one moving towards the center, and over here moving towards the center. The length of this arrow represents the number of G1 particles coming in, and I've got the same length over here. That's an assumption. It's an assumption. And as it goes through, if you remember my presentation on interactions, when the G1 particle passes through an object, it can bounce off of the object or it can be trapped by. So as it goes through, it keeps losing particles until you get over here, there's very few particles. Oh, I don't know how many. I have no numbers, but it's less than this, setting up a differential between the fewer particles pushing out versus the many particles pushing in, setting up a higher differential than you would expect when you didn't include this concept. So that force is there. Now what I'm going to do now is I'm going to switch around, and I'm going to explain using my hands, using these two arrows. And at the center, I'm going to say that they're approximately equal. So when we get to the center, they're equal number here, equal number here. But when they were at the edge of the galaxy, I've got to get these levels right. This is crazy. All right, there we go. And the height represents the amplitude, the number of particles. So as they come together at the core, they meet, and then as they continue, they're going to keep going down. So they start up here, they come down, and they meet. Now, at the center now, if you were to go this way, from the center out this way, when you go backwards this way, it increases. When you go forward this way, this one decreases. So as you go through the core, it moves over and up. Through the gap, it stays about the same. Through the first arm, over and up and down. Through the gap, the same. Then through the second arm, it gets even bigger. And that's the differential you have. This one up here represents a lot of particles. This one down here, very few, and it sets up a differential force pushing towards the galaxy. That's the particle model. Model says that's what happens when the G1 gravity, the graviton, passes through the galactic plane. That's going to happen. Now, that's only one. There are other paths. You've got to consider all of them. In a normal calculation, I would have done 38,400 calculations or paths, calculating each one through open space, through mass. Tough job, but it can be done. Okay, so now we move on to the next slide. So the particle model claims that there is a very high force of acceleration at the edge of the galaxy, and it is the same as if you were increasing g. That's the only way in Newton's gravity equation you can increase the acceleration. If you're not changing the distance, if you're not changing mass, you have to change g, and that's exactly what I'm saying happens. So g is the one that changes. So I take their equation, standard equation for velocity, and g is now varying over the galaxy. The value of g is greater at the edge. In fact, g varies with its location, and it is not constant. Particle model says the g is not constant. Now, I can actually use the blue curve. Interesting point. I can use the blue curve to calculate the value of g at any point. I rearranged the equation that I squared the velocity and rearranged it, and you come up with this equation where the value of g at any point is equal to the square of its velocity times the distance divided by the mass of the galaxy. So I'm going to calculate that. I took this curve. Now, admittedly, I don't have data points. Somebody had data points to begin with, and then they plotted this curve as a typical value, not a precise value, typical one. So this has already been adjusted from the true data. They took that and they plotted this. Then I took this, I made a hard copy, put a grid over it, and I read off of this data points. So that at each distance, I picked a velocity off of the chart. Picked the distance, check, got the velocity. That's a manual thing, so I don't have the raw data. I'm using somebody else's estimate of what the blue curve is, and then I'm doing a manual read. Makes it pretty iffy, but kind of interesting to try and do. When I replot those using a spreadsheet, this is what I get. It's kind of a piecewise linear approximation. You can see it's a straight line here. There's two straight lines here, and each one of these, a little chunk is a straight line. But you can see generally it has. But behind this curve are data points, specific velocities at specific distances. Then I use those data points. I use those data points to calculate the value of g at any given distance using this equation, where I'm assuming the mass of the galaxy is constant. Doesn't change. I'm not adding dark matter or anything else. I'm just using the blue curve to calculate that, doing that. Well, I went, this is the equation, and I did it for an object at some r0 distance that had a v0 velocity, and I'm comparing it to the g value at our solar system, because that's where we measure g. We know what that value is. The value of g at that point is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. It's a very strange number, but that's what that is. So I'm comparing, each one is compared to that, and I use the ratio of G0 to GS, and I come up with this equation, and that's how I calculated the value of G using the blue curve. And that's the value I get. I get a value of 0 at the core, and it goes up to very high, almost a value of over 20. 12, data point 12 is where our solar system is, and that's 6.67. And you can see some of the inflections. You can say, well, this is the core, this is the gap, this is the first arm, this is the gap, this is the second arm, and that's the rest of it. It's harder to see, but it's kind of there, but it's almost linear going out through the galaxy. You'd have to use, if you use these values of g at these distances, you could calculate the value and duplicate the core, the blue curve. I did something else. I actually turned the equation around. I used this equation. Instead of g equaling v squared r over m, I got m equals v squared r over g. Typical. This is the number I read in the internet, that the dark matter model says the mass of the galaxy is 6 times 10 to the 42 kilograms. Every data point, I recalculated the mass of the galaxy at every data point that I had selected from the graph, and they all came out identical, which it should. They're all the same. I assume mass was equal to the mass of the galaxy that our solar system sees. But the interesting point is the value. The value is less than the dark matter, but much greater than the, see, because 5% of this is visible matter. 5%. You divide this by 19 or 20, and you get a smaller number, but still very large. But because of the particle model and the fact that it loses force as it goes through, you don't need as much mass. Smaller number is expected. Whether that number is even right, I don't know. Don't know if it's right or not. Conclusion. Mainstream picked the wrong term in the equation. They picked M as something that had to increase, and they invented dark matter. And they did not explain the blue curve one bit. The particle model suggests that the force of gravity changes as you move from the core to the edge of the galaxy. And as a consequence, if you're going to use Newton's equation or Keplerian equation, you have to change G as you go through the galaxy, and G is neither universal nor is it a constant. And the model actually predicts the blue curve, which mainstream doesn't even talk about. The model predicts it. So this is very strong evidence that the theory of the particle model has some credibility. I can't prove by that blue curve that gravity is caused by a particle or a wave or space-time or something else. I can't prove that. I have no direct evidence. What we have is indirect evidence by this velocity that says the G changes. And the particle model explains on what the basis for that change in G. Particle model concludes G is not a constant and it can predict the blue curve. You decide. You're the critical thinker. Is G a universal constant, or does G vary by location? The particle model says yes, it varies by location, and dark matter is not needed. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I will explain more of the universe using the particle model. Thank you for your attention.